Hello, everyone. And thanks to the organizers for inviting me to give this talk, and thanks to you for watching it. As you can see, I'm not recording with the best light conditions, but hopefully this will be fine. So I talk about inflation and primordial cosmology, and I like to say that primordial cosmology is like a detective story. So inflation takes a tiny patch of space and stretches it to become the entire observable universe. And in that process, unavoidable quantum fluctuation also gets stretched, and they provide the seed of all the structures we have in the universe. So for a primordial cosmologist, literally any observation of the cosmic microwave background, the distribution of galaxies or gravitational wave backgrounds, give us a probe, more or less convoluted, of the statistical properties of the primordial fluctuations left over after inflation, primordial density fluctuations and primordial gravitational waves. And so in this detective story, we need data. Obviously, we need observational data, but we also need theoretical data to go from the physics of inflation to these properties. And that's not always easy, as I'll try to explain. So this is really exciting times for inflationary cosmology, I think. After Planck, there was no immediate motivation from observations. And actually, this led to a burst of new ideas for the future. In this talk, I will describe one aspect, which I like to refer to as precision physics, which is this idea of using non-Gaussianities as a cosmological collider. And there are other interesting aspects about inflation, and exploratory physics or more formal aspects that are really worth investigating, but that I will not be subject to this talk, but I'm happy to discuss this in the discussions. So here's the outline of the talk. First, I want to motivate the physics of the non-Gaussianities and the cosmological collider, then move on to discuss some recently developed approach, the cosmological flow, and then go on with applications. So let's begin with this first part, where in particular, I want to use a language not that often known of the effective field theory of inflationary fluctuations. So let's step back. In this detective story, what are the clues that we have so far? We know that the primordial fluctuations are adiabatic. So the different species in the universe fluctuate in the same way. This means that one can describe fluctuations with a single fluctuating scalar degree of freedom left over after inflation, which is usually called zeta, the curvature perturbation, which can be defined with this gauge. Then we can study the properties of this zeta fluctuation, and famously, its two-point function is almost scale invariant. This has been detected at more than 5 sigma by Planck, and this points to an approximate times translation invariance during inflation. So the Peirce spectrum is a power law with a slight deviation from scale invariance with an amplitude of order 10 to the -9, famously. The other thing that we know is that these primordial fluctuations are very Gaussian, which points to a weakly coupled theory during inflation. Indeed, we have tested the Gaussianity to better than 0.1%, which is remarkable. As for gravitational wave, well, famously they haven't been detected, so we only have upper bound on them. But it would be spectacular to detect them. This will identify the energy scale of inflation to be of order 10 to the 14 GeV, just 5 orders of magnitude below the Planck mass. And so it's really worth all the efforts, although it's fair to say that from a theoretical perspective, there is no useful theoretical lower bound on H and on the tensor to scalar ratio. So these BMOs may be forever out of reach, which is not problematic for inflation. In the rest of the talk, I will concentrate on density fluctuations for definiteless. And well, I told you that primordial fluctuations are pretty Gaussian, but I want to describe during the whole talk the effect beyond this. So primordial non-Gaussianities. And the idea is very simple, as most of you know. By looking at higher order correlators, 3-point function, connected 4-point function, etc., one measures the interactions of the fields active during inflation, exactly in the same way as what you do with colliders in particle physics when you want to know how particles interact. That's exactly what non-Gaussianities do for you in cosmology. And the goal is the same: establish a standard model of inflation. So identify the degrees of freedom active during inflation, their mass, their spin, their interactions. An additional difficulty compared to particle physics in all this analogy is that everything here, all concepts are a priori time dependent, which makes life richer, but also much more complex. So here is the language I wanted to introduce. This is now quite old, but maybe I'll take the time to review it because if you're not working on inflation, that's maybe something with which you are unfamiliar. The idea of this effective field theory of inflationary fluctuations is to forget the question of what was the source of inflation. Take for granted that something like inflation happened with an almost exponential expansion of the universe. And formulate theories straight at the level of fluctuations around that background. Of course, looking at specific sources of inflation can motivate specific EFT, and studying them can inform you about the source of inflation. But in this language, you focus straight on the fluctuations. The idea that it's very powerful because it's directly linked with observations, it's systematic, and it makes useful use of symmetries. So in this language, you see inflation as an example of a phenomenon of spontaneous symmetry breaking. Namely, imagine single field inflation where you have your scalar field. You can see it as a clock telling you when inflation has to end, when the scalar field reach a given value. And you can always go in a gauge where your inflaton is homogeneous. This would be the unitary gauge in that language. And going to another gauge or perturbing the field, you can introduce what is called this Goldstone boson pi here that can be seen as fluctuation of that clock field. What is important to remember from this is that this is the unavoidable degree of freedom guaranteed to exist during inflation, and that it is directly related to this variable zeta that we can constrain in the sky. And here's how it works. It's a bit technical, but I want this to be understood. The idea is that if you go in this gauge in which the inflaton is homogeneous, this unitary gauge, you can write an action with terms that are only invariant under spatial diffeomorphisms because you have selected a temporal gauge. And in this language, it has been shown that this first part of the action here, Einstein-Hilbert action, G00 part of the metric, which is invariant under spatial diffeomorphisms, all this is perfectly allowed, and this actually describes single field theory in these guys. And you can then add higher and higher order operators. For instance, the easiest one start with delta G00 squared and cube, etc., without derivative acting on the metric. There can also be more complicated objects like with extrinsic curvature. And this, if you want parameterize for you, all the deviations from single field slow roll, like effect of heavy fields or non-perturbative dynamics. So at that level, we haven't gained much because this looks pretty complicated. The idea is that one can actually restore the time diffeomorphism invariance by the so-called Stuckelberg trick. So taking that action and going from t to t plus pi, or pi transforming in a given manner, so that t plus pi is a scalar quantity. And well, a priori, you don't gain much at that stage because you had here the metric, you reintroduce another degree of freedom. The idea is actually when you look at observables that are not dominated by the mixing with gravity, you can actually take the decoupling limit in which your space-time metric is unperturbed, is de Sitter. And that's enough for most purposes. In that case, the perturbation of the G0 component of the matrix is delta G00 that enters here, becomes that object. And there is a linear part, there is a quadratic part. And that's one of the things that is important. This is related to this idea of nonlinear realized symmetry. So let's take the simplest paradigmatic example. Imagine that you have this delta G0 squared. This will generate a pi dot squared in the action that will add to this one, which effectively introduce a non-trivial speed of sound for pi, for this Goldstone boson. But in addition to that, you see that in the delta G0 squared, you will generate this mixed term pi dot t pi squared, which is this term, whose amplitude is fixed by the speed of sound. And that's the typical example of what the EFT of inflationary fluctuations bring you. Here, this non-linear symmetry of time, translation, and variance tells you that as soon as you have a low sound speed, you have boosting non-Gaussianities. So let's see how it works. The primary object is a 3-point function. Because of homogeneity and isotropy, this just depends on the configuration of triangles formed by these wave vectors. We can define the shape function S. Remember that AS here is the amplitude of the two-point function, 10 to the minus 9. And there are many information in this, much more than in two-point function, which depends on just one variable. The overall amplitude of that function is called the FNL parameter. And you can also look at the dependence of the signal on the scale dependence of the triangle. So in a perfectly scale invariant theory, there will be no dependence. That's mostly what I will concentrate on in this talk. But there is always an interesting information in the shape dependence, on the dependence on the configuration of triangles. And so in this prototype setup that I mentioned, these two different types of derivative interactions will generate shapes that are of the type equilateral. Namely, if you plot the two-dimensional information contained in this shape, famously they pick on equilateral triangles. The two are slightly different, so you can actually build two different templates, so-called equilateral and orthogonal non-Gaussianities. And they have been constrained by Planck, which gives lower bounds on the speed of sound, because FNL is not too large, it means the speed of sound cannot be too small. It's important to realize that we are far away from threshold for slower dynamics, which correspond to probing FNL of order 1, and we are even further away from the minimal level of non-Gaussianity in single field slower models, which corresponds to FNL of order 10 to the minus 2 or slower parameters. So that was for the simplest single field EFT of inflation with the unavoidable degree of freedom pi. But a very important idea during all this talk is that, well, given that Planck scale physics does not decouple during inflation, given all the high energy motivations coming from string theory or supergravity, or just because we want to be curious in the data, many people entertain the idea that one can look for all the degrees of freedom active during inflation, because indeed, well, in all these constructions, having a single degree of freedom driving inflations is somewhat baroque. And so the idea is how one can probe the existence of these other degrees of freedom. Well, first they have to mix with pi, because pi is what you observed. So if they are completely hidden sectors, you will see nothing. Of course, they mixed anyway, typically gravitationally. What people have understood is that you can probe additional degrees of freedom by going to soft limit, or for the three-point function, the squeeze limit, where one momentum k long is much less than the other two. And famously, in single clock inflation, the observable part of the squeeze limit goes to 0 like kappa. And as I will show you, this is not the case if you add all the degrees of freedom. So let's take as a simple example that I will use later on also, this action in the unitary gauge. Remember, everything is built with this delta G00 part of the metric. And now I'm adding also an extra scalar field sigma. This is really a fluctuating degree of freedom. This has no VEV, if you want, no background part. When you do the Struckelberg trick, remember that this will generate pi dot, but also this d pi squared. So this will generate both quadratic mixing between pi in blue and sigma in red, but also these cubic interactions. And so this sigma field on its own has its own kinetic and mass term here with a mass m. And I'm considering a scalar degree of freedom for simplicity. You can compute non-Gaussianities in this kind of setups with some dramatic rules, which correspond here to an exchange of this sigma field. What is important physically is that when you go to the squeeze limit with the hierarchies of scales between long and short modes, it means that you are sensitive to different times during inflation. Basically, the time of the vertices here appearing in this diagrams are sensitive to Hubble crossing for the short mode and for the long mode. And so effectively, what you are probing when you change the configuration of triangles is that you are probing the super Hubble evolution of that field sigma. And that's very important because that's related to, the behavior is related to the mass of that scalar field. And the physics of this is pretty simple. Here is the equation of motion of the scalar field in the super Hubble limit. And it's one line to derive the behavior to solve that equation. And a massless field would just stay there without decaying. A field with a mass greater than 0, but less than this threshold value, 3/2 of h, would decay with this power law with the exponent nu, whereas a massive field, in the sense of a mass greater than 3/2 of h, will decay, like 1/8 to the 3/2, with additional oscillations as a function of the number of E-fold. with a frequency mu that is also directly related to the mass. And so what is important is that this distinct behavior of the different masses of the scalar field imprints itself in the shape of the bispectrum in the squeeze limit with a specific power law, again related to the mass, or with a given power law, k to the 1/2 here, times oscillations with a given frequency, again detected by the mass. And you can see that this always beats the single clock signal that was going to zero like kappa. So the simplest thing to detect is if there is another light scalar field beyond pi, beyond the massless Goldstone boson. In that case, that's relatively easy to see because you have a large signal in the squeeze limit, so-called local shape. And the idea is to try to detect that via the famous scale-dependent bias FX that it leads to, and come back to it in the discussion. And quite importantly, as I said, this is not possible in single clock inflation. This would be a smoking gun of other light degrees of freedom during inflation. Well, we've seen now the three main shapes of non-Gaussianities: equilateral and orthogonal, about self-interactions of pi, and local, that will tell you the existence of another light degree of freedom. So there's been no detection from Planck, but there are huge efforts to improve these bounds and possibly detect non-Gaussianities with future CMB stage 4, with large-scale structure surveys like Euclid. In the long term, we can think about doing 21-centimeter radio astronomy from the far side of the moon and detect the minimal level of non-Gaussianity. Here is where we are. And this is, I think, is rather important. I told you that there was no minimal lower bound on the amplitude of primordial gravitational waves, which is not the case for non-Gaussianity. So there is a clear science case to go and improve experiments to try to measure that signal. Because either we found a non-minimal level of non-Gaussianity beyond this, and that's a sign of new physics, new degrees of freedom or new features, or either we confirm that minimal level of non-Gaussianity in its shape, and that's a triumph of the simplest models of inflation and of cosmology, both theoretical and observational, or we find no detection, and in that case, well, inflation would be ruled out. So it's always win-win, if you want. That was for the main type of non-Gaussianities. But remember, I told you that, well, depending on the specific mass of any particle coupled to the Goldstone boson, this does not necessarily go into the local shape. In particular, when you have a massive field with a mass greater than 3/2 of h, this leads to this specific shape with these oscillatory patterns. And people have understood that one can really read off the mass and the spin through the angular dependence here in theta of the heavy particle that was exchanged during inflation. So these heavy particles are produced spontaneously by the expansion of the universe, and later they decay. We do not observe them directly, but we can see their imprints in these specific oscillations in soft limits. This is valid for 3-point function, but also for 4-point function or other higher order correlators. And literally, this is the same as the way we detect particles in colliders. This is different in colliders. You do, let's say, a 2-2 scattering amplitude, and you vary the center of mass energy. And when you reach a given value, you create a resonance, and that's a sign that you have actually produced that particle on shell. Whereas if you are away from the resonance, you could look at the virtual effects of that heavy field by integrating out and end up with a single field effective field theory. And the same thing here. And in generic configurations, if you have a heavy field, you can integrate it out and end up with a simpler single field description, but that will always miss the fact that actually there is a little probability to generate even very heavy particles despite this suppression with a large mass here. And if you go to the squeeze limit, you are always sensitive to this and you can detect these heavy, very particles. But there's lots of work about this. And it's really huge. I mean, literally, this gives the possibility to detect particles of order of the Hubble scale, therefore, possibly billion times more massive than what you can do with the LHC. So it's really worth, it's really worth the efforts. Well, of course, I haven't covered at all the whole space of non-Gaussianities. Also beyond non-Gaussianity, there can be interesting physics in features, deviations from scale invariance, and so on and so forth. But really, if you step back a bit, the role of theorists is really to build a dictionary between the physics of inflation and, again, the statistical properties of the density fluctuations. And you can wonder, after 20 years of Gaussianity, whether this dictionary is complete, whether all the interesting targets have been identified. And as I'll try to explain, actually, this is not the case. So let me move to the second part about this cosmological flow technology that we've been developing with Denis Vert here and Lucas Pinot. And you can here see references. So the idea basically is we want to be able to compute correlators in any theory without technical difficulty. And for that, we can switch to a numerical approach. And the idea is to follow the time evolution of correlators during inflation for theories, again, that are formulated straight at the level of the EFT of inflationary fluctuations. So you can give us any theory with any number of degrees of freedom, with any coupling, any time-dependent sound speed masses. We can press enter and end up computing the final correlators at the end of inflation. So the idea is to shift from technical considerations of being able to compute correlators to just getting the result and having an unbiased exploration of what is possible during inflation. So this is what I will try to explain. So we know how to compute correlators during inflation. There is a well-known informalism. You take your given theory, you split it between a free part, the interaction part, and you treat these interactions in perturbation theory. And with this, through this well-known in formula, you can derive diagrammatic rules and perform computations. The thing is that these computations are hard. At any vertices, you would have to perform a time integral because you don't have time translation invariance like in particle physics. Also, because of the expansion of the universe, mode functions are typically very complicated. Instead of exponential, they become Hankel functions. And all that becomes very, very nasty, although in principle straightforward. There's been lots of recent analytical developments to try to compute with very different methods these cosmological correlators analytically. And there's been huge progress. But the point that we take with this cosmological flow approach is that these analytical methods will always have limitations. Typically, there are, of course, examples to this, but to give you an idea, typically what these analytical methods can do is to deal with nearly scale invariant theories, or to deal with situations in which you have a large hierarchies of masses and couplings, but they will not deal efficiently with intermediate regimes. Remember, I showed you this quadratic mixing between pi and an extra scalar field sigma. These quadratic mixing are often treated perturbatively in analytical approaches, which leads to many types of diagrams which are very complex to compute. And in general, there is no good theoretical motivation for this mixing to be weak, and we'd like to go beyond that. Also, typically, squeeze configurations and equilateral type configurations are treated separately. So because of all this, there's a kind of bias in the field of non-Gaussianities. So really the big picture is, so we like to understand the physics of the universe. For this, we need to have templates and accurate predictions to test against future data. But the thing is, because we have technical difficulties in computing these correlators, we limit ourselves typically to simple theories. And this is really bad because this can bias interpretation of data, because you can only look for things in the sky for which you have computed. And that's why we try to develop an approach that can compute correlators in any theory in a systematic and efficient manner without any approximation. And so here is the idea. The XA here are all the fluctuating degrees of freedom in your theory, pi, sigma, and actually also the conjugate momentum if you take a Hamiltonian point of view. All these quantities also carry a momentum index. They have a wave vector. They can be field of momentum, and they also have a wave vector index. So basically here, these are all the 2-point functions in the theory. Field, momentum, momentum for all the different species. And you can show that at tree level, you can derive a closed system of equations. All the two-point functions, their time derivative, are just related to all the other two-point functions in the theory in a way that can be systematically read off from the action. Same thing for the three-point function. Three-point function, its time evolution is governed by three-point functions and two-point functions that are known otherwise. So you can solve these equations very easily, numerically, kinematical configuration by kinematical configuration. So here, triangle by triangle. So we're not the first to use these methods. In particular, David Milroy and David Siri use this for a nonlinear sigma model of inflation, but we've been developing the technology with the FT of inflationary fluctuations in mind, in which you can take any theory formulated in that language. As I said, typically in analytical computations, the quadratic part of the Lagrangian is split into a diagonal part that you can solve, plus a mixing part that you treat in perturbation theory, leading to many diagrams and complexities. In this approach, these quadratic interactions are just part of the free Lagrangian. And so there is no need to actually, it's kind of as if all the two-point functions we're computing would correspond to resumming an infinite numbers of quadratic insertions if you are using a perturbative scheme to treat this mixing interactions. But there is no need for that here, and we can go beyond weak mixing. So really the idea is that with this tool, you can study, explore, and understand inflationary physics without technical difficulties. And in the several papers that I mentioned, we show examples of that. We can compute shapes of non-Gaussianities in different series, look at the cosmological collider signal, and derive new templates, look at the time evolution of correlators. And I will show you some examples of that in the rest of the talk. But really the idea is that, well, we made this for the community. Our code is public. It's easy to use. We've made all the work about coding, and in particular, student Denis Vert. And now you can literally take your favorite Lagrangian, press enter, and go and study physics. So happy to have your feedback about that during the discussion session. Right. Let's see how I got this time. That's fine. Now let's move on with applications of this cosmological flow approach to the cosmological collider physics and to something that I call the low-speed collider physics. So I explained to you this particular thing, right? You can see oscillations in the squeeze limit or specific angular dependence. You can read off the mass and the spin of the particle that were present during inflation. That's the standard law. It should be said, though, that this robust probe of the field concept of inflation, it's as robust as the assumptions are restrictive. This only is valid if you have pi coupled to a unique additional degree of freedom, weakly mixed in scale invariant series. In general, the situations may be much more complex. What you observe is pi, and you want to study kind of hidden sector, additional degrees of freedom. And first, they have to talk with pi, otherwise you will not observe them. And so in general, the whole signal can depend on, well, first, the properties of pi, like, for example, its speed of sound, but also on the mixing, of the type of the mixing, can depend on the strength of the mixing, weak, strong, its time dependence. As far as the hidden sector is concerned, you can have several degrees of freedom, not only one. You can have interaction in that sector. You can also have time dependencies. And so in generic situations, you can have much more diverse cosmological collider signals. And this has been studied, this dispersion relations in these different works. The time dependence in the hidden sector has been studied. And there's been many, many studies. I just want to quickly tell you some of the things we've been doing with collaborators. We were able to go beyond weak mixing. That's something I will talk about. Also giving different sound speed to pi or extra degrees of freedom, and having multiple degrees of freedom interacting. And here there is a nice analogy with neutrino flavor oscillation, and go and study a time-dependent mixing. So I'll try to discuss briefly these two stuff. So that's a very limited sample of the cosmological collider physics. A week ago, there was a nice workshop entirely on that subject. So you can have the slides, but I will describe very briefly some of my work on that subject. So remember the setup that I was describing of the FT of inflationary fluctuations. Here is the pi sector with the speed of sound. Here is this extra single massive degree of freedom, sigma. Here is this quadratic mixing, rho, which is the size of the coupling, it has dimension of energy, times pi dot sigma. Remember that there is always this nonlinear realized symmetry. So when you have this interaction, you necessarily have this one whose amplitude is fixed. In general, you can also have self-interactions of sigma and all these things that I described at lowest order in derivatives. And so in one of the long papers that I mentioned, we studied quite exhaustively this prototype setup for cosmological collider physics with this cosmological flow approach beyond weak mixing, also beyond scale invariance that I'm considering here first for simplicity. So one thing that I like to stress is if you go beyond weak mixing, you can show actually relatively easily that the frequency of the cosmological collider will not be governed by the bare mass m, by an effective mass, which is m squared plus rho squared. So weak mixing rho much less than m, you will see nothing, but when you go to large mixing, it's rather important. And indeed, here are cosmological collider results for heavy mass m, weakly mixed in blue, and a light field, small m compared to h, but strongly mixed field with the same frequency m effective, and therefore mu effective here. And you can see that, well, if you just look at the frequency of the signal, there is no way to see the difference between the two. However, with the cosmological flow approach, you can break these degeneracies by having complete predictions about the size of the signal, the phase, and so on and so forth. I try to move here to something else. Hopefully this will work. All right. So here are the time evolution of the cosmological collider signal for these two situations that I was describing, weak mixing and strong mixing with the same effective frequency. And you see actually how interesting it is to see the time evolution of correlators, because here you see the differences like an overdamped or underdamped oscillator. Here you read straight the final value, whereas here you overshoot. This kind of stuff are the typical interesting feedback you can get from the cosmological flow approach, which is you can identify characteristic time scales and not only generating the data, which would be the thing you observe in the end, which is with the dashed lines, but also understanding the physics of what's going on during inflation, which can help in designing templates and better understanding your theory. Let me stop this and come back to this slide. Oops. Sorry, that was a slight technical difficulty. So I just said that you can have a heavy but weakly mixed particle or light but strongly mixed that would give the same cosmological collider frequency. But there is actually a huge difference, which is if you have a weak mixing, you have a weak signal. However, at strong mixing, you have a much larger signal. So here the different curves correspond for different operators to the cosmological collider signal. So this plot corresponds to isocell triangles. Here you have equilateral triangles, squeeze limit, and these oscillations are the cosmological collider signal. And the mass is fixed to a few h, whereas the amplitude varies. And you see that for weak mixing in blue, you have small oscillations, whereas for rho over h over the 1 or 2, you have much larger signal, both for the background part, for the equilateral part, and for the cosmological collider physics. Something that I like to say very quickly, we also can go beyond scale invariance and look at a time-dependent mixing. What is important here is that we look at a mixing that, okay, has an overall power law as a function of the scale factor, but more importantly, it oscillates with a classical frequency omega c. And what we showed in that case is that, well, there can be really non-conventional cosmological collider. Remember that for a light field, you would have a given power law. Here, you can have actually for light field oscillations, in that case, governed by the frequency of your background mixing. Whereas for a heavy scalar field, instead of having oscillations related to the mass of the scalar field, you can have modulated oscillations with frequencies mu plus or minus mu c. And just quickly, technically, maybe for the experts here, and the idea is that that's quite visible in the FT approach. Remember, when you do the Struckelbeck trick, you go from t to t plus pi. So as soon as you have this operator that I mentioned, this necessarily generates for you also this other interaction. And it is this one that gives you these interesting signals corresponding to this template that I described quickly. And I can develop this more in the discussion session. Now, let me move with the last idea that I wanted to tell you in this talk, which is the methodology of what we call the low-speed collider. I have three things to tell you here very briefly. First one is that there is a striking non-Gaussian signature that has been missed for some reason for years, and that we identified. The second thing is that you can really understand its origin using a non-local effective field theory. And the third idea is that this can accommodate also for large parity evaluation from this emergent non-locality. So the first idea is following. Let's imagine that we detect equilateral non-Gaussianities in the future. So the simplest interpretation is that pi had a reduced speed of sound. Then you can say, what's next as a theorist? And what I told you that most people saw that, well, it's easy. You go to the squeeze limit. It's easy theoretically. You go to the squeeze limit. You hope to see oscillations typically, and you would deduce the existence of an additional massive field whose mass you can detect, you can pinpoint from the frequency. But what we showed actually is that in situations where pi has a reduced speed of sound, there is a much more visible signal through what we call this low-speed collider resonance that would arise for much less squeezed triangles and at a position of squeezeness that will tell you actually the mass of the scalar field. If you have the speed of sound from the equilateral part of the signal, the location of that bump will tell you the mass. And this happens in this situation because you have kind of two horizons. You have the usual Hubble horizon felt by this massive field that propagates with the speed of light, and you have a different horizon, the sun horizon felt by the Gaussian boson. So it can be a heavy field, but somehow still light compared to this new threshold value. Imagine that CS is 0.1, you can be a mass of order, let's say 2H or 3H, but still be light compared to this. That's the idea. And to see how you can visualize this, here are some diagrammatic rules to see how we can go on for simplicity in flat space. The idea is that because pi has a reduced speed of sound, the energies are related to physical momentum through this dispersion relation. Because of energy conservation, the energy here, omega, will be down compared to the momentum here by this factor of CS, which means in practice that you can forget that there was actually a degree of freedom propagating here. You can integrate out that heavy field. However, you should keep all this. Usually when you integrate out a field in theories with Lorentz invariance, both the time derivative and the gradient terms act in the same way. And therefore, you end up with effective field series in powers of 1 over m squared. Here, you have to actually keep this non-local terms, these gradient terms. And you end up with a single field theory, which is non-local. That's kind of, morally speaking, that kind of amounts to replacing the Feynman propagator by this instantaneous propagation of this supersonic field, and because of that, action at distance, and therefore a kind of special non-locality of Yukawa type, which is benign. And the third idea, and I want to tell you, is that you can play the same game, but now exchanging a massive spin one field with different helicities. In that case, you can play the same game, and you will end up with a single field non-local EFT, which can generate actually large parity odd 4-point function, which has been quite contributed in the literature in the last years. I have to wrap up if I want to stick with the schedule. So about this low-speed collider, what I wanted to tell is, well, in some simple situations, we can have exact bootstrap results. That's something that we did with Sadra, Jazairi. We also have exact numerical results with the cosmological flow approach, which you, again, as I said, you can have a transparent physical understanding of the physics of this through this non-local single field DFT. And here is in a few equations what I was telling you. Here is the equation of motion for the scalar field sourced by pi. And here, because of the breaking of Lorentz invariance, you can neglect time derivatives that scale like h, whereas you should keep special gradients because when they are evaluated at the typical time of sunrise and crossing, they are much, much bigger because they are larger, and hence by this factor 1 over CS squared. And therefore, you can integrate out that field through this non-local part, which is not only 1 over m squared, but 1 over m squared plus gradient. And you can see this criterion that I was already mentioning. If the mass is big enough, think that these gradients basically are of the side h squared over c squared. So if m is actually great, if this parameter alpha is greater than 1, you can actually integrate out the field in a local manner. But if this is less than 1, then it's crucial to keep these terms. And well, if you do that, you end up with a single field theory in which you can compute things pretty easily. At least at weak mixing, I don't want to be brief, but you can easily make analytical computations, and that's what we did. In these papers, you end up with simple templates that people already used to look for in the data. We use the cosmological flow approach in that framework to go beyond weak mixing, which is rather important for the observability of the signal. And here's a proof with cosmological flow that you can get interesting new shapes beyond, if you want, equilateral type shapes in red here. You can have this low speed collider resonance in addition to it, so that the total observable signal will have this weird new shape. And you can do that with full perturbative control. You can find these different ideas that I mentioned about the low speed collider in these 3 different papers with different aspects covered. So let me conclude here. Well, I mentioned a few things in this talk. I wanted to explain that there's a rich physics of the cosmological collider. Also beyond the linear models, you end up with several new motivated signals when the restrictive assumptions of a single degree of freedom, scale invariant, weak mixing is concerned. I've also described what I think is an interesting new target, which is low-speed collider resonance, which is also interesting anyway, just from a theoretical perspective when you think about these non-local DFTs. And well, overall non-Gaussianity after 20 years is a mature field, but it was still limited and biased by technical difficulties. That's why we developed this cosmological flow approach, which is systematic, which can generate data, for which you can explore the rich physics of inflation without technical difficulties. And I hope you will use it. I'm happy to discuss natural extension of this cosmological flow approach here that I just mentioned briefly. And here are a quick announcement about workshops and conferences that I'll organize next year with colleagues near Paris. So you can have a look. And well, thank you for your attention.